Today is Friday, the best day of the week, according to me. Of the working week, of course. Otherwise, it's Saturday. Okay, I see that people are still connecting. Very good. So today, let's look what we have to cover today. Let me open the calendar. Here we are. Okay, so today is March 4th. Time passed by so fast. So what we have gravitational potential energy, elastic potential energy, conservative versus non-conservative forces. And also, I think we need to cover, yes, we need to cover also this class here. So before that, we need to cover energy, work, and work energy theorem and power. Okay, so this will be mainly the topic of today, and probably we will cover a bit also of conservation of energy because they really go together with the previous topic. Okay. And then, so this is the last, next week is going to be the last week before spring break. So during spring break, you will have more time to focus on all these things and catch up with the things you haven't done yet. Now, let me open the slides. Let me stop share and share again so I feel more free. Bam, bam, bam. And share again. Okay. So yeah, I already put the slides on Laulima, so you can find all the slides. Actually, I put the slides up to the end of this course, so you shouldn't have any more this type of problems. Okay, so let's start with work. Let me remove this from my. Okay, so what is work? The definition of work is when the force is parallel to the displacement. So here you see you have the force, this guy that is pulling this, pushing actually this box in a certain direction. And because the force is in the parallel to the displacement, so we can define the work as the force multiplied by the displacement. Now the unit are in Newton per meter, which we define as joule. Okay, so if the force is at an angle with respect to the displacement, like for example in this case, the work is done only in the direction of the displacement. So here we are going to have that the work is force cosinus of theta d, okay? I don't know if like this you are able to see my pointer. Are you able to see my pointer? I cannot see it actually, so I prefer to do like that. Do you still see my slides well? I hope, because like this I can use the pointer. So only the horizontal component of the force does any work, okay? So we don't have any work in the y direction. Here is only on the x direction. So let me give you the examples. So the energy is transferred from person to spring as the person, for example, stretches the string. And this is what defines the work. So the work again is F delta X, because there is a displacement in this case. And in some cases, the force is all along the x-axis, as we said. So all the force and displacement provide the work, while when the force is as a certain angle, as already said, we only consider the component of the force along the displacement. The units, as we said before, is joule, which is Newton per meter, okay? For example, if I just stand and I keep a box in my, even if it's a big, heavy box in my arms, do I do work? No, because in this case, the displacement is 0. So if there is no displacement, work is equal to 0. Okay, so this is important. You need to have a displacement to have a work. So also in this case, oh, this is the dot product. Sorry, you haven't done that. So let's remove that. Otherwise it's confusing. So the work done might be positive, 0, or negative, depending on the angle between the force and the displacement. So let's see here, for example, in this case, we have a displacement in this direction. Is this force doing any work? The answer is no, because there is no component of this force along the displacement. So for example, here it could be this force, it could be the normal force. So in this case, the normal force is not doing any work because it's not along the displacement. If the displacement will be along y, then yes, there will be a work associated with it. Then in this case here, we have that the work is positive because we have here a certain angle. So it's F cos theta multiplied by D. And so in this case, the component of the force is positive, the displacement is positive, so the work is going to be positive. In this other case, instead, what we have that the displacement is positive, because you always remember the displacement and the forces are vectors, while, for example, the work is a scalar, okay? So it's not a vector. So here what we have that the displacement here is positive. The force is, in this case, has a negative component along x. So it has a positive component along y, but a negative component along x. And because what matters is the force that is parallel or along the displacement, the one along y doesn't matter. What it matters is this one, so along D. And so in this case, this one is going to be negative. And so we're going to have a negative work. Okay, let's see one example. Pulling a suitcase. We have a rope inclined upward at 45 degrees that pulls a suitcase through the airport. The tension of the rope is 20 Newton. So we have the force here, right? 20 Newton. How much does the tension do? How much work does the tension do if the suitcase is pulled 100 meters? So to make it work, we need to have a displacement. If the displacement will be 0, we would have 0 work, as we said before. But in this case, we have 100 meters. So x final minus x initial, which means delta x, is 100 meters. And then we say that we have 45 degrees angle with respect to the horizontal. We know that the work is only done along the displacement. So we have F cosinus of theta multiplied by the displacement, which gives 20 Newton multiplied by 100 meters, which is the displacement, cosinus of 40 degrees, which gives you 1,410 joule. Okay. Now, let's see other examples. If you have questions, just write in the chat, and everyone will reply to you. And then if there are questions that everyone needs to understand better, we will stop and we will see that particular question. So in this case, for example, remember when we discussed about the centripetal force, which is the force that is always directed towards the center when you are having a circular motion, remember? And we said it's always perpendicular to the displacement, always perpendicular to the velocity. So in this case, we have a car that is traveling on a curved highway. The force due to frictions points toward the center of the circular path. And then we said that the centripetal force can be also play the role by the friction, right? That keeps the car going along the circular motion. So in this case, we have that our friction is going towards the center. And although the car is changing constantly its direction, but also the friction is constantly changes its direction toward the center, right? So no matter where you consider this, you always have that the force is perpendicular to the displacement. So in this case, therefore, the work is 0. So a force that is everywhere perpendicular to the motion does not work, okay? I hope it's more clear for you. Now, we can have gravitational work. So here, if you have a person that is lifting up or open this hand and lifting up this object, and then opening the hands and let the gravity do its job, what we have is that we have a work done by the gravity, because what is going to happen to this object here is that it's going to fall down till the surface. So it's going to have M. So we're going to have the force, which we know is mg, right? And then the displacement is going to be h. So the work done is mgh. Is it okay? So if the object is subsequently allowed to fall a distance h, gravity does work. And the work is indicated with a capital W, which is equal to mgh on the object. Very good. Now, we might have also many forces on an object. So when we have many forces that are playing a role on an object, of course, we have that the total work is the sum of the single work done on this object. So here you see we have a force going in this direction. And so we are going to have a work. If there is a displacement, of course, there must be a delta x, which is different from 0. But what we are going to have is that if delta x is different from 0, then we are going to have the force in one direction that makes a work, plus the work done by the x component of this force, and plus the work done by the f components of this force. So essentially we have the x component of the force 1 delta x plus the x component of the force 2 multiplied by delta x plus the x component of the force 3 multiplied by delta x, and so on, depending how many forces they are. So if you do this, you can bring delta x outside, and so you can just do the net force along x multiplied by delta x. Okay. So are there questions on the chat?
There's one question about whether these quantities are magnitudes or not.
So this quantity is a scalar quantity, right? So it can be 0, it can be positive, it can be negative. It doesn't have a direction. So this is what it is, not a vector. If this is the question. So for example, in the example of before here, this work here might be positive or might be negative, depending how you select your x-axis, y-axis essentially. So if normally we select the y-axis going up, so in this case, the work will be negative because you will have minus 9.8. But if you select the y-axis going down, it will be positive. I don't know if this responds to the question. Okay. So let's do another example. So maybe the things will become more clear. We have a 3,000 kilogram truck that is to be loaded onto a ship by a crane that exerts an upward force of 31 kilonewton on the track. This force, which is large enough to overcome the gravitational force and keep the track moving upward, is applied over a distance of 2 meters. Find the work done on the track by the crane. Okay, so here we have the work done on the track by the crane. We have work. We know that is the force along the displacement multiplied by the displacement itself. So the force is all along the displacement because it's all along y and is 31 kilonewton multiplied by the displacement, which is 2 meters, gives you 62 kilojoule. Okay, so this is the force, the work done on the track by the crane. Then find the work done on the track by gravity. In this case, what we have the gravitational force mg delta y. So in this case, we have the weight, the mass of the mass of the track, 3,000 kilograms, minus 9.81 meter per second square, and this is the gravity force, multiplied by the displacement, which is 2 meters, you get a negative work, okay? Because indeed here the force, as you see, for gravity is going down, okay? While the y-axis is going up, so it's considered negative. The net, find the net work done on the track. The net one, what is going to be? Is going to be the sum of the work done by the crane plus the sum plus the work done by gravity. So 62 kilojoule plus minus 58.9 kilojoules, which is equal to 3.1 kilojoules. So I hope that these examples make you understand a bit better the concept. Are there any questions on these things?
Yeah, Veronica, on a previous slide did the formula define work as equal to force times displacement times cosine of the angle between force and displacement? Okay, so in the case of the weight, right, the weight force points downward and the displacement of the truck is upward, right?
Yes.
So we have a displacement vector that's up, we have a force vector that's down. So what that means is in this particular case, the value of phi of theta is 180 degrees. So that's where the minus sign comes from. Cosine of 180 degrees is -1. So in case anyone's wondering, the force is equal to m times g. This is the displacement here, right? I should use S because it's what I drew over on the right. And then the minus sign comes from the cosine of 180. Okay, great. Thank you.
Okay. And then I see here a question that doesn't negative quantities indicate vectors? No, vectors. No, vectors, negative quantities are just negative quantities. So it's no.
Yeah, scalars can be positive or negative.
Can be positive and negative.
Right.
Zero
Scalars
positive and negative, as we said before. And vectors, it depends on the direction. And so at the end, they can also be positive and negative and zero. So yes. So what is the vector? The difference is that we did it last time. So for example, those are vectors because you have components along X, components along Y. So it's You need to have the magnitude and you have to have a direction. And the magnitude is always positive and the direction is what define if it's positive or negative. So let's see the work energy theorem. The total work done on an object is equal to the change in the kinetic energy. So the kinetic energy is defined as 1/2 mv square, velocity at the square. And the change in the kinetic energy, of course, is 1/2 mv final square minus 1/2 mv initial square. So this theorem is telling you that the total work is equal to the change in kinetic energy. So we have two ways to define the work. The other one was a force time displacement, while this, in this case, we have that is equal to the change in the kinetic energy. So, and it's very powerful because now you'll see it allows us to solve a different type of problems. So let me show you. For example, here you pull a sled of a mass of 80 kilograms with the force of 180 Newton at 40 degrees above the horizontal. The sled moved delta x, which is equal to 5 meters, starting from rest. Assume that there is no friction. Then find the work you do and find the final speed of your sled. Okay, so this is the picture. It shows a normal force, it shows the weight, and then it shows the force here with a certain angle that we know that is 40 degrees. Okay, now here it shows the initial position and the final position. So we have a delta x in this direction. We start from rest, it says, and we are going to assume that this is 0, and it moves of 5 meters. So the final position is 5 meters in this direction, okay? Find the work you do. So is there any work along the done by the weight and the neutral and the normal force? No, because there is no displacement along y. The displacement is only along x. So what we need to consider, these two, we essentially do not care. We only consider the components of the force along x. So we are going to have F cos theta delta x. So we're going to have 180 Newton cos theta, which is 40 degrees, cosinus of 40 degrees, multiplied by 5 meters, which give you 689 joule. Indeed, we have Newton and we have meters, and Newtons times meters, we know that is joule. Okay, perfect. We also have the proper unit. And this is the answer to the part A. In the part B, it says, find the final speed of your sled. So to be able to find the final speed, you need to use the work energy theorem. So you know the work, and you know that is equal to the change in the kinetic energy. The kinetic energy is related to the velocity, as you can see from this one. So just applying that theorem, we have that the total work is equal to 1/2 mass V final to the square minus 1/2 mass V initial to the square. V initial, we know that is starting from rest. So the initial velocity is equal to 0. So we have that this expression is equal to 1/2 m V final to the square. So V final to the square is equal to 2 times the work divided by the mass of the object. So the square root of 2 times the work divided by the mass. You do the calculations, blah, 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 and you find 4.15 meters per second. Okay, so this is a typical example where you use the work and where you use the work energy theorem. let's see another one. Stop me if there are questions, or if I go too fast, let me know. So this other one, instead, we want to take a displacement along the y-axis. So we have a 150,000 kilogram rocket, which is launched straight up. The rocket engine generates a thrust of 4×10⁶ Newton. What is the rocket speed at the height of 500 meters? And it says ignore air resistance and mass loss due to burnt fuel. Of course, we need to consider very simplified case, right? So let's see what we have. And I suggest you, when the problem do not provide this drawing with this information, you just do it. Do a simple thing. You just make this as a box or as a point, whatever you prefer, but make the initial situation and final situation. So in the initial situation, what we are in 0. Okay, we have an initial velocity which is 0, and we said y naught is equal to 0. Okay. Then we are in the final situation where we have 500 meters and we are a V1. So what we are asking is actually V1. Okay, this is what we are looking for. What are the forces that are playing a role here? So we have gravity, and it's going down, as we know. And then we have the thrust, the force of the thrust, which is provided here. Okay, very good. So to find the final velocity, we need to use the work energy theorem. So we first find the work made by the thrust. The work made by the thrust is force of the thrust delta y, which is equal to 4 × 10⁶ Newton multiplied by 500 meters, and it gives you 2 × 10⁹ joule. Okay, so this is the work done by the thrust. Now let's see the work done by gravity. So again, as explained before, Mike, we have this cosinus of theta, and because it's 180 degrees, this brings you a minus. So we have minus mg delta y. Okay, so we have minus 1.5 × 10⁴ kilograms, which is the weight of the mass of the rocket, multiplied by 9.80 meters per second square, multiplied by 500 meters. And so we have this, okay? This is the work done by gravity. Then what we know is that the change in the kinetic energy, so 1/2 mv final to the square minus 1/2 mv initial to the square, but we know that the initial velocity is 0, so this is 0, is equal to the work done. The total work done is the work done on the thrust plus the work done on the gravity, and so is this one minus this one. So if you perform all the calculations, you find that the velocity is equal to this value. Okay, so here they are not all the calculations are shown, but it's pretty straightforward. So this one minus this one gives this value. Okay, and then if you want to find the velocity, delta k is equal to this value, so you can find 2 delta k divided by the mass, which is your the expression for the velocity, and so you find 129.6 meters per second. Let me know if it's not clear. Okay, it's just solving this equation, so you know how to do that, I'm sure. Okay, so power, we can define another quantity, which is power, and is a measure of the rate at which work is done. So is the work divided by the time. And this is provided, so the units are joule divided by seconds, and this is defined as watt. And I'm sure you have seen it many times in all the electronic device that you are using, or in the car, as you see, hours power is 746 watt. And this is another definition. So let's see another example. We have a 500-gram ice hockey puck that slides across a frictionless ice with an initial speed of 2 meters per second. Okay, so this is our hockey puck, 500 grams. This is frictionless with an initial speed of 2 meters per second. Okay, a compressed air gun is used to exert a continuous force of 1 Newton on the puck to slow it down as it moves 0.550 meters. The air gun is aimed at the front edge of the puck with the compressed air flow 30 degrees below the horizontal. Okay, so we have this puck, which is going in this direction with a certain velocity, with an initial speed. And then we try to stop this puck with an air gun that is aimed here at the front with the force, with an initial force that flows with the compressed air flow 30 degrees below the horizontal. So this is the horizontal, and this is going to be 30 degrees. So of course, this one is going to be 150 degrees, okay? Because this is 30 degrees too. Okay, very good. What is the puck's final speed? Okay, so we have here the initial situation is initial position 0 meters, initial velocity 2 meters per second. The mass is 0.50 kilograms. The force applied is 1 Newton. Then we arrived after a certain displacement, which is 0.5 meters, and we need to find the final speed. Okay, the final velocity. So we have that the work is equal to F delta R cosinus of theta. So the force is 1 Newton, the displacement is 0.5 meter, and then we have cosinus of 150 degrees. If we do all this calculation, we find that the work along X is minus 0.433 joule, okay? And you can see this because indeed the component of the force here along X is in the opposite direction of the displacement. So of course you have something that is negative, okay? Then we have the delta K is 1/2 mv1 to the square minus 1/2 mv0 to the square. And this is equal to the work. I hear someone talking. Okay, so from this, we can find the final velocity, which is equal to the square root of the initial velocity to the square plus 2 times the work divided by the mass. Okay, so here I just isolate this. I bring this on the other side, and then I divide it by the mass and multiply by 2. And so it comes out with this. And so now I know everything because this was provided 2 meters per second to the square, because it's velocity to the square, plus 2 times the work that I just found divided by 0.5 kilogram. So here the only difficulties, if you want, was to be able to identify this cosinus of 150, okay, to identify the component of the force along the displacement. I hope it's okay. Are there questions that yeah, the kinetic energy is 1/2 is indicated not with 0.5, but with 1/2 mv square. Yes, this is defined as the kinetic energy. And delta K, the delta of the kinetic energy, is V final, 1/2 mv square final minus 1/2 m V initial to the square. So this is the, yeah, how is defined, the kinetic energy. Okay, let's see another example. In a television picture tube, electrons are accelerated by an electron gun. The force that accelerates the electron in an electric is an electric force due to the electric field in the gun. An electron is accelerated from rest by an electron gun to an energy of 2.5 keV, which means 2,500 electron volt, over a distance of 2.5 centimeter. And it tells you here that 1 electron volt is 1.6 10 to the minus 19 joule. Find the force of the electron, assuming that it's constant and in the direction of the electron's motion. Okay, so the force is constant and in the direction of the electron's motion. Okay, so in this case, we need to find the force. We know that the total work is equal to delta K. So we have that total work, we know that is the force multiplied by delta X. Delta K is K final minus K initial. And so from this, we can find that the force is equal to K final minus K initial divided by delta X. K final, we know because it's 2.5 2,500 electron volt multiplied by this quantity to be able to find joule, minus 0 because the initial one is equal to 0 divided by delta X, which is in this case 0.025 meters. Okay, so in this case, the energy we know is the kinetic energy, right? So here is providing the energy, the kinetic energy, and you need to find the force. So it's just a different usage of the same formulas.
Veronica, could I add one
Yes.
quick thing? So so everybody notice that newtons are the MKS unit of force. So if we're going to wind up with newtons here at the end, we need to make sure that everything we plug in is also in MKS units. So note we were given centimeters up in the description of the problem, but we have to convert that into meters when we plug it in. Also, we're given the energy, the kinetic energy of the electron in these weird units called, electron volts, EVs. Okay? You'll see those a lot more in physics 152. We use them a lot in physics 152 because the amount of energy used that electrons and protons have is so tiny that using joules is cumbersome, right? So we end up using this much smaller. But notice how we have to convert the electron volts into joules when we plug it in to the expression. So that's what this is right here.
Yes.
Yeah, so that's the only way to ensure that our final units are going to be in MKS units of newtons, is if everything we plug in gets converted also into MKS units.
Yes. And you see it because you see that these units are the units that you normally use. So yeah, so when it's like this, of course, the problem is giving you the extra load of being able to convert the units. Okay, so now let's see a spring. We have a 4-kilogram block on a frictionless surface, which is attached to an horizontal spring with K, 400 Newton per meter. You remember the constant for the spring? 400 Newton per meter. The spring is initially compressed to 5 centimeters. Sorry, I need to drink. I cannot, I really need to drink. One second. Okay, I'm back. Can you hear me? So
Yes, great. Thanks.
the spring is initially compressed to 5 centimeters. Find the work done on the block by the spring as the blocks move from -5 centimeters to its equilibrium position at 0 centimeter. And then find the speed of the block at x2 equal to 0 centimeter. Okay, so it might be scary at the beginning, but let's see what we need to do. So we have 4 kilograms block. So we know the mass of this block. We know that it's frictionless, so this is easier. Then we know K, 400 Newton per meter. And we know that the spring is, but we didn't define this. Did you define this in your lecture, Mike's?
No, not yet. So I think
The
that's
kinetic energy for the springs?
the potential energy stored in a spring.
Because I don't know if it's too advanced.
That, well, it's part of this chapter. So it's in this chapter, but I think it's discussed with the
Mike, can
potential
you
energy
hear
of
me?
gravity.
Oh, I cannot hear you.
It's
No.
so we can't derive this for students because that would require an integral. So in this chapter, in chapter 7, everyone is simply told that the potential energy stored in a spring is equal to 1/2 kx squared, where
Yes.
x is how far the spring is stretched or compressed from the equilibrium.
Yeah. So we defined it. Okay, I just wanted to make sure that we already defined this on the lectures. Okay, very good. So we can use, in this case, we can use our usual work energy theorem. So as Mike said, we know that the potential energy associated with the spring is 1/2 kx squared, where x is the displacement. So in this case, we have 1/2 kx 1 to the square minus 1/2 kx2 to the square. And this is equal to the work. And work in this case is the force along x, which is our spring, is the only one that is playing a role along x, multiplied by delta x. So the force of the spring is minus kx. I don't know if you remember from the previous lectures, is minus kx. So minus kx delta x is equal to the difference in the potential energy. So here we have 1/2, doing all these calculations comes to 1/2 400 Newton per meters multiplied by the displacement, which is minus 0.05 meter to the square minus 0 meter to the square, which gives you 0.50 joule. If then it says find the speed of the block at 0 centimeters, which means in the final position. So we have that the work is 1/2 mv final to the square minus 1/2 mv initial to the square. And so we have that v final to the square is equal to this expression. We saw it already before. Because v initial is 0, we can just write that v final is equal to the square root of 2 times the work divided by n. The work we find it before, so I just plug the the number that we found before, and 4 kilograms is the mass, and I found the final velocity. Okay. So this is an example in the case we have the spring. So for the spring is always a bit more tricky in the sense that you have the X twice. One time is because of the force, and another time is because of the displacement, delta X. So here there are some problem solving strategy, and you can read those when you are at home. And then what I want to do, I want to discuss conservative force, for example, gravity. The work done by gravity in a closed path is 0. So if we look here, a closed path A, B, C, and D, we have that the work done from A to B is 0 because there is no displacement along the X. So the work here is 0. From B to C, the work is minus mgh, right? Because we have that the force is going in this direction and the displacement is going in this other direction, and the displacement is going in this other direction. So minus mgh. From C to D, we have 0 work, while from D to A, we have the displacement, the gravity are in the same direction, and so we have work is mgh. If I sum up all these values, we have 0 minus mgh plus 0 plus mgh, so the total work is 0. And when the total work in a closed path is equal to 0, that force is conservative. Non-conservative force, for example, is a friction. So the work done by friction on a closed path is a non-zero. So here we are moving A to B to C to D on the top of the floor with the friction. We know that the friction is always opposite to the displacement. So here we have minus mu K mgd. In this other case, we have minus mu K mgd. Here, minus mu K mgd and minus mu K mgd. So in all of these, we see that if you sum up all these works done, this is not 0. So the work done by a conservative force is 0 in any closed path. This is the definition. And in this case, the work is stored in the form of energy that can be released at a later time. An example of conservative forces are gravity and spring, while an example of non-conservative force, for example, is friction. And with this,
in fact, those are the only 2 conservative forces we've learned up to this point, and that we will learn in physics 151.
Yes.
Gravity and springs, right? The elastic force.
Yes.
All the other conservative forces, like electric force or magnetic force, are in 152.
So we define as a gravitational potential energy, we indicated with minus delta U, the work done by gravity, so mgy. So is in this case is minus delta U because we do U initial minus U final, as you see here. And okay, so the work is U initial minus U final, which means minus U final minus U initial, which means minus delta U. This is the definition of our potential energy. So if we pick up a ball and put it on a shelf, we have done work on the ball, because to put it on the shelf, we do work, that we can get that energy back if the ball falls back off the shelf. In the meantime, we say that the energy is stored as potential energy. So as you see, there is a conservation of energy. The potential energy can be associated with any conservative force. And so for the gravitational, we just saw it now, delta U gravitational is mgy final minus mgy initial, while for the spring, the conservative, the potential energy of a spring is u final minus u initial, which means minus the work done. So is minus 1/2 k x final to the square minus 1/2 k x initial to the square. Okay, so I think with this, we have pretty much done. There are a few more examples that I put in this lecture that we can do on Monday.
Yeah, I agree.
Yeah.
Yeah. I think maybe Monday we can review potential energy quickly and then show some conservation of energy examples.
Yes.
Yeah, perfect.
Okay. Were there questions? So yeah, U stands for potential energy. W stands for work, and K stands for kinetic energy. Okay, so have a great weekend, everyone. And I'll see you on Monday. Thank you so much.